Everybody, peace and love. We're here for physical geography lecture. This is Unit 19, the human impacts on climate change or anthropogenic climate change, or what you may have thought before you read Unit 18 and listened to the lecture from 18, climate change in general. As we know, we've gone in the order of talking about natural climate change first, and that it's a real thing and something that we have to take into consideration when we think of climate change collectively, and not just really just treat it as if it's 100% human caused. However, there's a reason why we have an entire chapter devoted to the human impact on the climate, because it is a serious issue and it is something that we have factual data to back up many of the arguments made in favor of it. So, yeah, let's go ahead and talk about that now, um, and begin. So, eh, climate change really is first, mentioned before. Climate is not just specific weather events, local weather, or even daily weather extremes, yearly extremes, even decade extremes. It's not quite enough. Those patterns aren't quite extensive enough to be considered part of the climate or change to the climate. So we're really talking significant amount of time here, and we're going to go ahead and break that down now. Last week we said in the tens of thousands of years, this natural climate change is in the 20s of thousands of years, 21,000 years or so, between these cycles, glacial, interglacial cycles, and then even more so we have hot house, ice house. We're talking millions of years, right? So now we're down more into a more specific, or a tighter, shorter duration of time now in this case, because we have seen some extremes occurring over those short periods that we want to highlight. And the term global warming is an important piece that we need to focus on, because global warming, it's the term that refers to observed temperatures increasing over 150-year span, roughly. Okay, so even going back to um, technology and how human beings were able to record ambient air temperature and document that on a consistent basis and have some kind of standardization to that throughout the world. You're going back, about this time frame, and so it's when people started to document what temperature was really on a regular basis, and we're referring to, not like they knew back then, but um, since we have these records going back to this time frame, now we can see that there is a general trend of temperature increasing. Um, and the thing is that's interesting is that this is a very short period of time compared to what we were talking about in Unit 18. However, we're seeing the amount of change at that same level, if not even more so, in terms of warming compared to the much longer time frame. So that's what we're going to really dig into here. And so global warming is the temperature increase, and anthropogenic means human beings, and human caused. So anthropogenic climate change, kind of a more scientific way of saying what people are doing to the earth and how humans are contributing to this phenomena. um, it's a way of separating what people do versus what's going to happen naturally with Milankovitch cycles and changes in tilt and orbits, etc. Right? So anthropogenic climate change would be really the technical term we want to use. And uh, last unit we talked about the different scenes within the interglacial period, and so this current era that we're in, or time frame that we're in, this 150 years, we call that the Anthropocene. The Anthropocene. Well, anthro being the root word to that, or the root prefix to that word. So Anthropocene would be a new era where human impact on global climates has been significant. Okay, so it's like we've entered into an unprecedented territory, where for the first time in the Earth's history, there is an unnatural factor. I guess you could say Mother Nature is not the one that's actually contributing to Mother Nature, space, orbits, access, things that are completely out of control of human beings. Now this is 100% controlled by humans or caused by humans, the Anthropocene. Okay. Now, the two mechanisms have the potential to affect change. Okay. And I think this should be the two mechanisms that have had the potential to affect change. So the things that have caused, these are like the catalyst, the things that really got this Anthropocene kind of going, in a sense. And so first thing would be the way humans started modifying the earth and modifying the land surfaces, and what the characteristics of the land, what they were like, what they were like. We're talking about cutting down forests and, things like changing the way um, uh, rivers and lakes and dammed, and the way they're dammed up and things like this nature. And how about, of course, impervious surface like concrete and asphalt and streets and sidewalks, those kind of things. Um, all of those are human influenced changes to the characteristics of the land surface itself. So, um, when forests are cut down and they're replaced by agricultural land, there's a shift and there's a change in the energy balance. Um, and it changes the amount of moisture that's balanced as well. Okay. Um, and in not a good way in this sense. And so the same is true, but even more extreme when we talk about how impervious surface, when they are laid out on a terrain, especially if it's like there was a forest there before, and now we have an asphalt parking lot. You're talking about major changes to not only the amount of radiation that's absorbed in the earth, because you have black asphalt is very absorbent. You have a loss of um, uh, um, oxygen emitting plants and trees. And then you also have a change in the way that moisture, or the way that condensation is run off, right, from the rain and from water. And so it's a whole different balance now, or a whole different things get out of balance compared to what they would be naturally. Yeah, so those would be modifications to the land. That's the first thing we want to mention here. And then the second thing that we want to mention, human impacts on change to the atmosphere. Yeah, this is something called the Anthropocene hypothesis, when human beings actually started making changes to the atmosphere, intentional or not. That's through pollution and through byproduct and waste of a bunch of things we're going to mention here: machines, cars, etc. But according to the Anthropocene hypothesis, um, carbon dioxide and methane began to abnormally increase about 8,000 years ago. Okay, and we'll see here momentarily that carbon dioxide, number one, is extremely harmful when it comes to an atmospheric, something that we add to the atmosphere, and methane just as much so, but just in different volumes. Anyways, yeah. So this hypothesis says that when carbon dioxide and methane started to increase, um, uh, this is when we started to see some of this shift. You know, the increase of the carbon dioxide and methane occurred when, according to the hypothesis, when agriculture began to expand. When agriculture began to expand. So, to me, what I would sum that up as is I would say that the Anthropocene, um, human-caused climate change, really began with the expansion of agriculture. Um, some would argue it's the Industrial Revolution, which was only a few hundred years ago, which certainly has its place in how it contributed, because the Industrial Revolution was a time frame of, burning what we're going to learn here in a moment, fossil fuels for energy and automation, machines, etc. And absolutely, the Industrial Revolution um, really ramped this um, carbon dioxide addition to the atmosphere uh, by a large order of magnitude. But it wasn't necessarily the thing that started everything. According to the hypothesis, it would be the expansion of agriculture being the first thing to get things, going there. Um, yeah, I mean that's what people were. If there was more than just farmlands being planted, you're talking about forests being cutting down, and so that's where you have this imbalance of both one and two mechanisms in this case taking effect. Okay, um, let's see. So since the 1900s, there's been direct observations of air temperature, and they provide unambiguous evidence of change. So basically, that means that it is conclusive that there is change in air temperature over, 100, 120, 150 years. And we're observing that. And we're observing that the temperatures, this is globally, okay, global average of temperatures have increased by an average of about 1.8 degrees Fahrenheit since the early 1900s. Almost 2 degrees Fahrenheit of increase that becomes the normal over a very, very short period of time. Okay. So I'm just kind of throwing out some stats here to back up these arguments that the observations are making a case that the temperature is increasing. 2014, the warmest year on record, right? Collective warmest years on record have all occurred since the year 2000. So that means that over the last 20 years, we're seeing almost every year breaking the next record. So these records are meant to kind of last for quite some time. That's the whole point of them being a record. But they are constantly being, upended by the following year. Yeah, let's take a look at the slide number 8. Okay, so there's a lot going on there. Surface and air, yeah, it looks very extreme, obviously, but what we're looking at is adjusted temperature from, this is up to the 1970s, and then where we have the kind of the upward correlation there, increasing of temperature, we're seeing definitely a correlation of after the 70s, and again, like I said, this has been since the early 1900s, even going back further than that, but especially in more recently, the temperature is getting even more increased, increasing even more so. So the trend is that things are getting more like this, okay? Instead of just kind of at a gradual slope, things are going more like this. And so recent decades, we are observing that the thickness of Arctic sea ice in the North Pole is decreasing significantly, and that's from satellite photos and observing those year after year after year. Um, Literally with eyeball tests, noticing that the ice is kind of shrinking inwards. Okay, melting inwards on itself. Um, let's see how that looks. Okay, so looking at 100-year time frame from 1885 to, and again, this is more of a model simulation, but it would be based on not just the satellite photos and but actual measurements and scientific data. But that 100-year time frame, there's a definite decrease in the amount of white here, and projected based on current trends, we see something like this, where it's almost like there's no sea ice at all in the North Pole. It's scary stuff. This is the kind of stuff you see on nature programs all the time, and um, could be that polar bears end up being not polar bears anymore. They end up being um, well, I hate to say, unfortunately, extinct, or they migrate to lower latitudes, to survive. Who knows? Okay. Other things to mention here. Um, so we saw warmest records occurring in the last 20 years or so, and we also had a decrease in the number of extreme cold events, and an increase in the amount of extreme warm ones. That's not to say that there are no extreme cold events, because climate change is meant to say not just global warming, but also um, extreme weather events. So it could be extreme storms, hurricanes, hail, snow, that kind of thing. Um, Nevertheless, the trend is a warming trend. Okay, when we talk about the change of the climate, um, yeah, 30 years. Average glacier has lost an equivalent of 49 feet of ice depth. So another visual here. Okay, so yeah, here's some of those examples we're talking about. Um, Satellite photos, really showing some of this extreme differences. This would be from a drought. Um, that's part of climate change, right? Dry versus wet weather phenomena. In only about a 20-year span. That's not a very long time for an entire sea to go away. Um, here's more so what we're looking at. Again, from the model from the last glacial maximum to what currently things look like in 2012. Um, Anyways, okay. I do want to mention something important, and that is that global warming, it doesn't mean, even though I've been mentioning kind of things on average for the whole globe, over the last kind of bullet points I was mentioning there. I do want to say one thing, and it's an important thing to know, is that um, global warming does not mean that the temperature is increasing uniformly across the entire globe. Okay, so it doesn't mean that just because there's a 3-degree change in California, that there's also a 3-degree change in South America or something like that, right? It's not uniformal. It's not all the same everywhere. So that means that uh, uh, not every single place is even warmed at all. So nor does it mean that every place has warmed. Some places haven't even warmed at all, right? What we're talking about was an average across the entire globe. Whereas some places were much more than 1.8 degrees, much more than 1.8 degrees, and some places are much lower than 1.8 degrees change Fahrenheit since the 1900s. Reason being, so we look at the northern hemisphere, and there are much more extreme these increases in temperature in the northern hemisphere Well, because the northern hemisphere has the majority of the land masses on it, and so that idea that we learned weeks ago called continent continentality, um, basically land gets much warmer than water does, and also the second thing is, well, people live on the land, and so when there's more people there, then there's more um, like we mentioned the mechanisms before, and so the more people there are, the increased effect that the anthropogenic factor plays into this. So that means an increased urbanization and agriculture, both things, right? Really any kind of human activities per se are causing increases in greenhouse gases, which are making, in particular, the northern hemisphere warm much more so than the southern hemisphere. Nevertheless, it's still a global problem. Okay. Um, okay. Now let's take a look at a couple other things. Okay, this is a long one, but group called the Intergovernmental Panel on Climate Change, or IPCC, panel commissioned by the World Meteorological Organization, charged with the task of summarizing scientific knowledge related to climate change. Okay, so that is really the most collective scientific resource that we have across the entire world for what's happening with climate change everywhere. Okay, and so really, when we talk about scientists are supposed to be not biased and are supposed to, kind of as an oath that personal opinion, um, etc. They are intended to be completely um, objective, right? Objective. So they have no agenda, and that's why it's important. Because if they have a certain agenda, then they no longer kind of meet the standards what actual science is, just the facts. So according to this group, the IPCC, there is a less than 1% chance that human impacted climate change is false. Let me repeat that. Less than 1% chance that human impacted climate change is false. So basically, it's very, very unlikely that, so like a double negative, right? It's very unlikely that human caused climate change is false. So 99% sure that climate change is true. That's climate change by human beings is true. That's what the IPCC, just as a conclusion, there's much more that they do other than just that. But um, yeah. Okay, so this is the big one, and we talked about the mechanisms before, and this is the one that you're going to hear over and over again, because it is important, but it's also something that's quite political, and polarizing, and needs to be discussed amongst every single person, really, and as it is an important element to daily life and what future generations have to deal with, etc. So um, what we're getting into is why does this happen, and the anthropogenic release of carbon. Okay, carbon, we mentioned carbon dioxide and methane. So carbon into the atmosphere is a result of burning, big word here, fossil fuels, um, burning fossil fuels. So carbon, the release of carbon, okay, this carbon dioxide going into the atmosphere and uh, staying in the atmosphere. And the way that that carbon gets released into the atmosphere is by human beings burning what's known as fossil fuels. Okay, the most common fossil fuels, are coal, oil, and natural gas. Okay, coal, oil, natural gas. Those are the three big fossil fuels that I want you to remember from this unit. Okay, so when these three elements are burned, okay, that is the number one contribution of carbon release into the atmosphere, which we'll see here in a moment why that is such a detriment. Okay, let's see, what does this slide look like? This is an island, Mauna carbon dioxide concentration, and demonstrating since the 1950s, carbon dioxide parts per million. Again, remember, carbon dioxide, for all intents and purposes, is a trace gas, and it's a very, very small part of the actual atmosphere itself as an element. But still, relatively speaking, the amount of carbon dioxide is increasing almost twofold in some places. And what we're seeing here is, 50 years ago, we had 300 parts per million. And if we extended this graph all the way out to 2020, I could imagine that it's already up to 400 parts per million. So we're talking a 33% increase in this one little island alone, right? And they're probably not even the ones causing or releasing this carbon into the atmosphere. It could be coming from other parts of the world. That's why this is such an important global issue, because if factories in China are emitting carbon by burning fossil fuels, well, that carbon could stick around in the atmosphere and actually blow over to the United States, or blow into somewhere else, or blow to the Arctic and absorb radiation, which is going to melt the ice and increase the temperature. So anyways, currently, trends as we're seeing, and it's a very unique time in a sense also as I'm recording this to you guys, because we're experiencing COVID-19, and people kind of aren't burning as many fossil fuels, right? Oil prices are at record lows. People aren't traveling. People aren't going outside of their house, or they're not supposed to, and so gas prices are going way down, meaning that people are just not buying it. The demand is very low, and basically what's happening is we're seeing some of the even in visuals on the news, you're seeing kind of air quality vastly improve, where things before were not even able to be visually seen. But this is written in the sense of current fossil fuel release, meaning before COVID-19, right? Who knows what's going to happen after that? I guess if you're watching this years later, we'll see. But current anthropogenic fossil fuels, they release about 100 times more than that of what naturally happens with the gases from volcanoes. So that's the thing. When volcanoes erupt, they give off carbon, right? Same type of thing as burning gas from your car. But with what human beings are doing, it's like we have 100 times the amount of volcanoes releasing carbon into the air with the amount of fossil fuels that we're burning in our daily lives. So I have to let my cat out. Hold on 1 second. Okay, come on. There we go. Now, we are talking an estimate of 500 billion metric tons of carbon. Let me back up. The estimate is that about 500 billion metric tons of carbon remain on the Earth. That's a lot, right? This is all mostly in the form of coal. So all of the coal reserves on Earth estimated that there is still 500 billion metric tons of carbon. What that's going to do to the Earth and what that's going to do to the atmosphere, I mean, it can only get worse based on the trends we're looking at here. So what we're going to do now, as I bring my intern up to the video, is I'm going to show the video that we watched actually previously in Unit 5 about solar radiation, because it was very good demonstrating the greenhouse gases, and in particular, we already learned about how the atmosphere acts as a blanket and kind of keeps things temperature-wise balanced, on Earth and habitable for people and for the biosphere. But what I want to show it again, and I want you guys to really pay attention to now, are the particular molecules and how those molecules really focus on the fact that they do absorb that long wave radiation and they keep it in. And so if we increase those molecules, i.e. from burning fossil fuels, we're going to have this temperature increase. Let's try that now.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable negative 18 degrees Celsius. And even deadlier, they range from negative 170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder. Thanks so much to the great team over at Kurzgesagt for doing the animations in this video.
Okay, so like we learned there, the atmosphere, it's that blanket, and really what's happening here when we add more carbon, and all of those types of greenhouse gases for that matter, but in particular carbon from fossil fuels, it's like we're making the blanket thicker, and we just keep making it thicker and thicker and thicker, and the thicker you make it, the warmer you're going to get, right? So the more it's going to absorb instead of release into outer space. Moving on, there's something called general circulation models, or GCMs. And so these are computer programs, and they're designed to model various Earth systems with as much realism as possible. So this is basically models that are meant to predict what's going to happen with the atmosphere. So, looking at the models, and the thing about models is they're just data driven, and if there is any modification to the data, then the model is going to change as well, right? And so, looking at a GCM model that shows rapid warming of the atmosphere, or GCM models, they show that the rapid warming of the atmosphere, it actually disappears. It goes away when the anthropogenic factors are eliminated. So basically, when people aren't here anymore, right? And the anthropogenic factors are eliminated, and we remove those from the equation. Let's still run the model. What ends up happening is that the Earth should actually be cooling instead of warming. So there's even more proof based on these circulation models that, again, people are definitely having an impact on what's happening, okay? And an impact in a very, very short period of time. The time frame is really the thing that is giving us the conclusive answer to say, yes, this is a human impacted anthropogenic cause, okay? Um, let's see. So, feedbacks are amplifying global warming. And actually, here, before I do that, let's look at 13 and 12 quickly. Okay, global mean temperatures observed and simulated by GCMs that include both natural and anthropogenic. Not really sure actually what that's trying to tell us. Oh, here we go. Duh. Okay. So we have the anthropogenic in the red line and the natural factors in the blue line, meaning that I guess this is an observation. It's just looking at temperatures, I guess, right? But yeah, blue showing that things should be decreasing a little bit, if anything. Look, to sum it up, the models show that we shouldn't see the increase, at least the extreme increase that we're seeing so rapidly, um, in particular over the last, and it just gets worse. It just gets more extreme and more extreme as every year goes by. So, the water in the atmosphere that GCMs are showing that water in the atmosphere has a higher saturation point and therefore can hold more moisture. Or, I'm sorry, that the atmosphere has a higher saturation point, and it can hold more moisture. And so that's a problem also. We just watched in that video that water vapor is a greenhouse gas. Water vapor is another thing that contributes to um, uh, global warming because it can absorb terrestrial radiation, and that's not that's part of the problem. And so that means if the temperature gets warmer, that the saturation, how much water it can hold, can increase, meaning that if it holds more water, that the temperature is going to get warmer, and so this is just like a never-ending cycle, almost, in a sense. So this increase in moisture contributes to anthropogenic warming. We call that a positive feedback called a water vapor feedback. Okay, the water vapor feedback. All right. There's so many things we could talk about this, and I really wish we were in person to do this, because it's one of those things that you want to kind of get people's real feeling as they are making eye contact with the person. But I want to kind of close this up, and we'll do that with a video. But I want to ask you guys, what do you think? Should we believe in climate change? Should we believe in climate change? To me, there's two parts to this. We have to ask and answer this in two ways. So number one, has science identified a credible threat? Okay. Has science identified that something is wrong? And that something being wrong is, has science identified that temperature is increasing or temperature is changing? And in this case, what science has revealed is that temperature is increasing at very high orders of magnitude. Okay, so the answer, is there a credible threat? Then the threat is yes, absolutely. It's a unanimous yes. Okay, and 99% sure yes. Number two, are the associated risks to social are the associated risks to social disruption acceptable? So is it okay for temperature to increase like this? Is that okay for our society? Um, Again, these are answers to do we believe in climate change? And the answer is, again, this is just what I feel. So I'm really want to know your feelings as well. And I'll just tell you right now, I'm going to ask you this as an essay question for this unit. So to me, we're in society, and we'll take precautions. We take precautions for events, even if we don't believe they will occur with certainty. Like I said, IPCC has a 99% 99% conclusion or chance that climate change is caused by humans. Okay, and so you could certainly make the argument and say, well, it's not 100%. It's not 100% conclusion. But what I'm trying to make here, the point is that even if we don't believe in something with 100% certainty, we still take precautions. Like, I'm getting in my car and I'm gonna go drive somewhere. There's no certainty that I'm gonna get in a car wreck, right? But I'm gonna take the precaution, and I'm gonna put a seatbelt on, right? So that's a precaution. God forbid, hopefully, I don't get in a car wreck, right? So what I'm saying is, as a society, we already do those kind of precautions anyways. So even if there is that 1% chance that all this natural and anthropogenic climate change is totally false, it's still part of human nature and part of our society, based on the facts that we have, that we should be taking some type of precautions. Okay, some type of precautions. Again, as this becomes a political type of thing, what are those precautions and what does that really mean? And that's kind of where I want to hear from you, what you think, right? Because I could just give you my opinion all day, but that's not really the important part here. I want to hear from you. 17 and 18. Okay. Yeah. So the probability, right? The probability. You cross a busy freeway blindfolded, and it's very likely. Okay. The terminology is important. It's very likely that you'll be hit by a car or a truck or seriously injured or killed, but it's not 100% sure. Okay. Look, I don't even know exactly what the author's trying to make in particular with that, how that relates per se, but many things are not 100% sure, I guess. In this case, human caused climate change, anthropogenic climate change. We don't know 100% that it is. There's still like a little bit of doubt, but nevertheless, it is very, very, very likely the case based on the facts and the evidence that science is proving. That's going to be it from me. So I'm going to go away now. I'm going to show this last video, and then I'll go ahead and close this lecture. So I hope you enjoyed that. I hope you learned something. And as always, hit me on the discussion board and talk to each other, collaborate, and enjoy the rest of this video that I have to show. Take care, everybody.
Activities, from pollution to overpopulation, are driving up the Earth's temperature and fundamentally changing the world around us. The main cause is a phenomenon known as the greenhouse effect. Gases in the atmosphere, such as water vapor, carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, let the sun's light in, but keep some of the heat from escaping, like the glass walls of a greenhouse. The more greenhouse gases in the atmosphere, the more heat gets trapped, strengthening the greenhouse effect and increasing the Earth's temperature. Human activities, like the burning of fossil fuels, have increased the amount of CO2 in the atmosphere by more than a third since the Industrial Revolution. The rapid increase in greenhouse gases in the atmosphere has warmed the planet at an alarming rate. While Earth's climate has fluctuated in the past, atmospheric carbon dioxide hasn't reached today's levels in hundreds of thousands of years. Climate change has consequences for our oceans, our weather, our food sources, and our health. Ice sheets, such as Greenland and Antarctica, are melting. The extra water that was once held in glaciers causes sea levels to rise and spills out of the oceans, flooding coastal regions. Warmer temperatures also make weather more extreme. This means not only more intense major storms, floods, and heavy snowfall, but also longer and more frequent droughts. These changes in weather pose challenges. Growing crops becomes more difficult. The areas where plants and animals can live shift, and water supplies are diminished. In addition to creating new agricultural challenges, climate change can directly affect people's physical health. In urban areas, the warmer atmosphere creates an environment that traps and increases the amount of smog. This is because smog contains ozone particles, which increase rapidly at higher temperatures. Exposure to higher levels of smog can cause health problems such as asthma, heart disease, and lung cancer. While the rapid rate of climate change is caused by humans, humans are also the ones who can combat it. If we work to replace fossil fuels with renewable energy sources like solar and wind, which don't produce greenhouse gas emissions, we might still be able to prevent some of the worst effects of climate change.